Okay, welcome to the bonus lecture. This is going to be probably the most bonus lecture of all the bonus lectures. This is going to be a little bit of an advanced topic, but still it's, I think, important because we danced around this topic in a couple of places. And one of them was we were given a random variable and the corresponding probability density function of that random variable, or probability mass function of that random variable. Note that I'm going to be showing in this lecture the subscript of the probability mass function, whether it's going to be x or something else. You are going to see why I do it. And we were given a deterministic relation, such as this one, a functional relation between x and y. And we usually ask the question, what is the expected value of y? What is the expected value of y, and what is the variance of y? And what we did was we found the expected value of x using the probability mass function and variance of x, and then we have converted the expected value of y and variance of y using the properties of expectation operator and variance operator on this function, and we have come up with some result. And this was the first time that we have met this concept. The second time we met with the concept of dealing with the distribution of the function of random variables was through standardization. We standardized, we named a standardized normal distributed random variable z by standardizing a normal distributed random variable x through multiplying by a constant and subtracting from another constant. So we can easily think about it as ax minus b. But this a and b as special constants, which is actually standard deviation of the distribution, where this is the mean of the distribution. Anyway, the important point here is, now I'm not interested in expected value of z and variance of z, but the distribution of z. And I said that when we have normal distribution x here, the linear combination or the linear function of this normal distribution is still going to be normal. And note that this needs a proof, but I just skipped. So here, basically, the question is, the more general question is distribution of a function of a random variable. So we have a random variable here, x. We have a function. It may be linear, it may be nonlinear, any function that you like. We are going to be obtaining y. Then we are going to be asking questions about y. What is going to be the distribution of y? This is the question at hand. So to answer this question, we look from this perspective. We are given these quantities. We are given x, a random variable. We are given a support of x with non-zero, a domain of x with non-zero probability, and we are given a probability distribution function of x, whether it's discrete or whether it's continuous. And then we are given y through a deterministic function. And this y and support of y can be easily found using this deterministic function. You put the values of x here, you can find the values of y with non-zero probabilities. Why? Because these x from the support of x have non-zero probabilities. Therefore, corresponding to these x values, we are going to have y values with non-zero probabilities. But even at this point, there should be a one-to-one mapping here. I'm going to be talking about it in a couple of minutes. For each x value, there should be a unique y value. If two different x values goes to the same y value, then we are going to have a problem. So corresponding to that was y values, we need this quantity. And here we are given these and this one. It is easier to find y and support of y using this deterministic function. What we do not know and we need to find is this probability density or distribution function here. So I'm going to start with actually a theorem. Let's call it theorem 1. It's very easy. and it's very intuitive, but maybe the notation will look a little bit awkward. So we have a probability, the cumulative distribution function of x. So this is going to be the probability, that's all, let's remember the meaning, probability that x is smaller equals x. This is going to be equal to, in the probability distribution function of x, we are, instead of x, we are going to write the corresponding y value. And how do I obtain the corresponding y value? Very simple. If this is a function, this is a mapping from x to y, the mapping from y to x can be shown by this representation. So if you take the inverse of this function, actually, this is shown this way, g of x, g to the power minus 1 y. This is going to be unity. So this is actually, this goes back to your high school knowledge, I guess. This is going to be x. So, but instead of x, I'm going to be writing g to the power minus 1 y. And here is the thing here. You should think about what these mean in terms of mathematical entities, not just x's and y's. This means we have a function of x here. This cumulative distribution function is going to be a function in terms of x. However, in terms of x, we are going to be placing a function of y. Therefore, it's going to correspond to a specific value of y. So the whole function will be actually a function of y. So this is the result. The cumulative distribution function of x in the cumulative distribution function of x in the cumulative distribution function related with x is going to be equal to y in the cumulative distribution function of y, where x and y relation is given by this, this function representation given here. Now, when we have the discrete case, we are going to have, so let me write here, theorem 2b. That was the cumulative distribution function. Now, if we would like to talk about probability mass or probability density function, and this is going to be for the discrete case, so this is going to be for the probability mass function. Fx, probability mass function of x, of any value of x evaluated in probability mass function of x. This is going to be equal to the corresponding value of x evaluated by a given y value through using g to the power minus 1. This is going to be, note that it's going to give the same value of x still. But if you leave it as y, this whole thing using the same logic will still be a function of y. Therefore, this is going to be our required probability mass function of y. Therefore, our probability mass function of y, what we are interested in, will be found using this expression. What we are going to simply do is, inside the probability mass function of x, instead of x, we are going to write g to the power minus 1, and that's all. That's that much simple. Now let me show you on an example, and you are going to see that this whole thing is pretty straightforward. All right, so an example. Let's say that we have x binomial distributed with 5 number of trials and probability is 0.2. Let's say that these are kind of a competition like those on TV shows. You have 5 different competitions, contests, and you have 0.2 of winning those contests, each of them independent from each other. And we are interested in the total number of contests that you have win. And depending on the total number of contests that you have win, you win this much of money. So if you win none of the games, even just because of just entering the competition, you earn 2,000 units of money. But if you win each competition, if you win one, it's going to be 2,500. If you win 5 of them, it's going to be 4,500. So now let's write the support of x. Support of x is going to be equal to these values, right? It is due to the binomial distribution. Now support of y and I'm just using still this deterministic relation, is going to be 2,000. And when you win one game, it's going to be 2,500, 3,000, if you two of those, 3,500, 4,000, and 4,500. All right. Now the question here is, what is going to be these two quantities? And what kind of a typical question I may ask? For instance, I am given this information and I want to compute, I'm in need of money, and I want to compute what is the probability that I'm going to be winning more than, let's say, I would like to compute this. What is the probability that I'm going to be winning more than 4,000 liras or dollars or euros, whatever you would like to think about this one. And note that it's going to be basically equal to probability of, let's get rid of this equal sign so it's going to be easier. Oops. Yeah. Actually, this is going to be equal to 1 minus cumulative probability distribution function of, but these are going to be y. Or I might be just asking what is the probability of me winning 4,500 Turkish lira. Okay, so in order to compute these kind of questions, I need to find this. So therefore, the question is, given this information, find these probability distribution functions. Well, probability distribution function of x is going to be equal to 5 choose x. Probability of winning is 0.2, so 0.2 to the power x, and 0.8 to the power 5 minus x. That's much simple. And then let's see, starting using this relation I have shown on the other page. This one. Can I show it to you? Let me see. Yes, I can. I'm going to be using this relation. fxx is going to be equal to fx. Now I need g to the power minus 1. Can I obtain it? Yes, it's very straightforward. Now going from here, y is equal to gx. So x is going to be g to the power minus y. So it's going to be equal to y minus 2,000 divided by 500. That's that much easy. So I write it here, y minus 2,000 divided by 500. That's it. And that theorem says that this is going to be the cumulative probability distribution function of fy. So this function itself. And you may not believe me. Let's show it on an example. Let's say that x is equal to 1. I would like to find the probability that I win at least one game. This is going to be equal to fx1, because actually this is going to be equal to, note that probability of x is equal to 0 plus probability of x is equal to 1. So I'm going to be talking about actually this case and this case. Therefore, I'm going to be talking about in terms of y, this case and this case. So let's continue and see where this is going to lead to. So this is going to be equal to, I'm just going to be using this representation, fx instead y minus 2,000 minus 500. All right. Now this quantity is equal to 1. So actually, this means that probability of y minus 2,000 over 500 is smaller equal to 1, which is going to be probability of y smaller equal to 2,500, which is equal to fy 2,500. So fx1 is equal to fy 2,500. This is exactly what we are just using the support of the x and y, what we have found. X smaller equal 1 corresponds to this one, and y smaller equal 2000 is going to correspond to this case and this case. Therefore, the probabilities are going to be equal to each other. So that's how we can show that the cumulative distribution functions are equivalent to each other. Now, what about the probability mass function? Fx x is going to be equal to fx. Instead of x, I'm going to be writing again the form of the g to the power -1 representation of x, this one. And if I continue with the calculation, it's going to be, instead of let's recall what fx was. It was n over x probability x 1 minus p n to the power -x. That was the idea. So now instead of n, John, I'm going to just write the numbers. 5. Instead of x, I'm going to be write this expression is going to be 2000 divided by 500. Then p is 0.2 to the power. Now x is this whole quantity, y minus 2500, and 0.8 is n minus y minus 2500. I think that's okay. And we have n, I think here 5. And I can make this look nicer. Let me write it in this fashion. I think it's going to be better. This is going to be 5 over 500 minus 2000 over 500 is going to be equal to 4. And if I do the same thing here, it's going to be y over 500 minus plus 4 is going to be, so this is going to be 9 minus this value. Well, all of this doesn't look very nice. Still, this is going to be the distribution function that we have. So, and this is going to be fyy. So this is the probability distribution, a probability mass function of y. For any y value, we can compute this. For instance, f, let's say, y 2000. This is going to be 5. If you put 2000 here, it's going to be 0. If you put again 2000 there, it's going to be 4 minus 4, 0. If you put 2000 there, it's going to be 0.8. It's going to be 5. This is going to be 0.8 to the power 5. And note that this is exactly equal to fx being equal to, let's go back to the whole thing, fx 0. Because actually, if we go back to, let me see if I can find the, I think it was this one. Yeah, this one. 2000 corresponds to 0 winning game. Therefore, 0 winning game probability should be equal to that probability. And as you can see, it works very nicely. And if I can find the correct page, that would be even better. Okay, this is not the correct page. I have to be, yeah, seems like the correct page. So, and for other values of y, for instance, the question was, what is the probability of winning, let's say, 5,000 liras? I think that's not possible because it's not in the support of y. The largest value that I can win is 4,500. You should do the computation. Now, one important point, one can easily say that, what about this value? Note that you cannot compute, or this is equal to 0, because you should take one of the values. Since it's a discrete distribution, when we were talking about x, it was pretty much straightforward because x increased by 1. When we are talking about y, y does not increase by 1. It starts from 2000. The next discrete value that y can take is 2,500. It cannot take any value between those two. The y values between those two is not within the support of y. Therefore, 4,525, that probability is going to be 0. So actually, you should change, for non-zero probabilities, you should take one of the members in the support of y. That's the important thing. All right. Well, I thought of solving another question with Poisson distribution, but I think that's pretty much sufficient. So now let me continue with, Shandan, let me open another one. Maybe we are going to use some of these with theorem 2b. Theorem 2b is for the continuous case. For the continuous case, this result is a bit tricky. Now, what we call FYY, okay, let me, this is going to be, because in theorem 2a or in theorem 1, what we have found was the equality of cumulative distribution functions. Let me go back to that if I can find the correct one. I think that was it. Yes, that was it. What we have shown in theorem 1 was the cumulative distribution function here and here are identical. Now we are interested in density function, not probability mass function. And how can we go from cumulative distribution function to density function? We are going to take the derivative. Now that's the tricky part. When we take the derivative, I think that was, yeah. Let's remember what the derivative is going to be. If we are given a probability cumulative distribution function, if this is a differentiable function here, if you take if you take derivative with respect to y, you are going to end up with this value. Now the important point here is this: we are going to be using, instead of this y, we are going to be using some other thing, or we should do some other trick here. So let's see what we are going to do. This is going to be basically equal to why? Because if you go back one step further, this can be represented by this representation. Because if you recall, this all came back from fx. Instead of x, we have written this expression. And then since this whole expression is a function of y, this turned into a cumulative distribution function of y. Now here is the important point. Actually, since this part is actually, well, what I would like to do is, I would like to write here something like the probability density function of x. So an x here, the derivative with respect to x would have been very handy. So what I do is I use the chain rule. I first divide with respect to x, then I divide it with multiply by dx over dy. And let's go one step further here. Dx over dy, x, I'm going to write x as g to the power minus 1. So it's going to be basically this expression, dg to the power 1 minus 1 y over dy. And this derivation, and now note that this part is going to be, if you consider this as x, this is simply a probability density function of x. However, evaluated for g to the power minus 1. So this makes a very nice representation. It simply says that probability density function of x, just instead of x, replace the function g to the power minus 1 y here and multiply it by this function. But here we have one small problem. Note that since this is a probability density function, this should be always non-negative. Therefore, the quantity that we are multiplying, since this is going to be actually non-negative because we have a probability density function here, but this one is problematic. Actually, a negative slope can easily make this negative. Therefore, we put an absolute value here. Of course, the idea is not that much simple. I'm going to just mention that at the end very little bit, but the theorem 2b finalizes in this form. In absolute values. So the probability density function of the transformed y is equal to the probability density function of x evaluated at the corresponding y value multiplied by the derivative of this g to the power minus 1. Let's try to solve an example and see how this is used. Let me use the same page here, and it's going to make, I think, life easier. So let's say that as an example, all right, we have a uniform distribution. Defined between 10 and 50. And the corresponding probability density function value is going to be 1 over 40. And let's materialize this, for come up with a scenario for this. Let's say this is the time of working hours for a ChE or something like this. Okay, make up in a story. So what we have here is time of working hours is going to be the probability density function is 1 over 40, and the support of x is going to be between 40 and 10 and 50 hours. And now here is the function. Y is, let's call it the amount of money he or she gains is shown with this expression. So when just 10 hours is spent, no money is obtained. But if you work more and more, there's going to be quadratic increase in money. And now note that when x is equal to 10, y is equal to 0. So y is going to be between 0 and, when x is equal to 50, this is going to be equal to 1,600. So this is going to be the support of y. Therefore, we are going to be transforming x to y, and what we are interested in here is the probability density function of y. Because here for the, I think for the continuous case is much more interesting. The question is simply, for instance, if what is the probability that that person is going to make money greater than, let's say, 1,000 liras, dollars, whatever. In this case, what we need to do is from 1,000 to the highest amount of money, 600, we need fy y dy. This integral is what we need. And to compute this integral, we need probability density function. Well, it is a good practice to show the relation between x and y to understand or to appreciate the transformation idea better. What we have is something like this. From 10 to 50, these are the support of x, and the corresponding y values is going to be something like this, where this is going to correspond to 1,600. So what we are asking, actually we know the distribution here in terms of x. It's this distribution and it's uniform. The question is, what's going to be the distribution here? So between 20 and 10, there is actually this, the identical probabilities. There is a constant probability of working between 10 and 20, for instance. But what about y? If you just between 0 to 800 and 800, 1,600, there are equal probabilities. Actually, no. Think about like this. From 10 to 20, we have identical probability, and 20 to 30, identical probability. So these two probabilities are identical to each other. So therefore, and if we have 30 here, probability here of y between these two and y between those two should be identical. So probability of having a larger income as you go up is going to be for identically with identical widths, the probability is going to be lower. So I would like you to appreciate this transformation. Anyway, so what we do is simply we are going to be using this rule. Very easy. Fx, it is actually easier than it seems. What we always need to do is first to find g to the power minus 1. So it's going to be, if you take the square root of both sides, it's going to be square root of y is going to be equal to x minus 10, and then x is going to be equal to square root of y plus 10. This is going to be a function of y, as you can see. So instead of x, I'm going to be using this expression. Therefore, fx, I'm going to be the first, this first term here is going to be written as g to the power minus y, is going to be written as just 1 over 40, nothing else, because this is not a function of x. Therefore, whatever the value of y is going to be 1 over 40. What about this one? I need to take the derivative here. So d is going to be g to the power minus 1. I'm sorry, g to the power here. dy is going to be equal to, there's going to be a square root here, y to the power 1 over 2. So it's going to be 1 over 2 y 1 over 2. And note that we need the absolute value here. So I put the absolute value here. Therefore, I need not worry about the sign here. Although this is already positive, it could have been negative. So let me put that way. If there were a negative sign here, then it would be, of course, it would be then the amount of money maybe being lost, then would be the case. It will go in the other direction. Still, in terms of probability, we would use the same thing because we would be using the absolute sign here. Anyway, let's go. Okay, let's finish the whole thing here. So I'm going to be using, I have found this expression here. So I'm going to be combining those two. So what I do here is going to be simply, let's see, if y is going to be equal to 1 over 40 times 2 times y to the power 2. So it's going to be 1 over 80 square root of y. And y is going to be between 0 and 1,600. So this is the probability density function of y. And this is going to be the support of y. Actually, if you draw the probability density function of y, this is what you are going to more or less obtain. Y f y, probability density function, not cumulative density, the distribution function. Note that is going to be something like this. 1,000, this is going to be, the corresponding value is going to be equal to 1 over 80 times square root of 1,000. I think 40 is going to be 3,200, something like this, I guess. Yeah. So depending on whichever the probability you would like to find, for instance, if you would like to find the probability that you are going to be winning more than 1,000, then you have to be integrating for this part. It's going to be, integral is going to be from 1,000 to 1,600. It's going to be 1 over 80 times, so just take out 1 over square root of y dy and do the algebra.